Imagine a big toy box where you keep different kinds of toys, cars, dolls, blocks, and puzzles. Instead of dumping all toys in one huge heap, you put each kind in its own small box inside the big toy box. In a computer, a program's memory is split into segments that act like those small boxes, one for code, one for data, one for the stack, etc. Segmentation is needed because different parts of a program have different rules. The code box is read only, the data box is read write, and the stack box grows and shrinks as functions are called. By separating them, the operating system can protect each part, make loading easier. You can load just the code box, and let programmers think in logical groups, instead of a single long line of memory. A logical address in segmentation looks like two pieces of a puzzle: a segment number and an offset inside that segment. Think of the segment number as the name of the small box. Code box equals segment 2, and the offset as how far you have to walk inside that box to find your toy. Example, 120 bytes from the start. In binary, the address might be written as segment offset. For example, with a 16-bit segment field and a 16-bit offset, the address 3000300, a 0 means segment 3 160 bytes into that segment. This two-part address lets programs refer to memory without needing to know where the segment actually lives in the computer's physical RAM. When the computer really wants to use a toy, it has to know where the small box sits inside the big toy box. The operating system stores a base register, the start address of the segment, in physical RAM, and a limit register, the size of the segment. To turn a logical address, segment, offset, into a physical address, the CPU adds the offset to the base. Before doing that, it checks the offset against the limit. If offset is less than limit, the access is allowed, otherwise it is illegal. If 0 less than or equal to offset and offset less than limit, then physical equals base plus offset, else raise segmentation fault. This base limit check stops a program from reaching into another segment's toys, just like a child's parent would stop them from opening the neighbor's toy box. Explanation: a segmentation fault is the computer's way of saying you tried to reach outside the box. When the offset is larger than the limit, the hardware generates an exception. The operating system catches this exception and usually kills the program, printing a message like segmentation fault core dumped. Protection works because each segment can have its own permissions: read, write, execute. If a program tries to write into a read-only code segment, the hardware again raises an exception. This is similar to a librarian who lets you read a book but not write in the margins. If you try, the librarian stops you. Now imagine each small box segment is still too big to fit neatly on the shelf, so we cut every box into equal-sized pages, like dividing a bookshelf into fixed-size slots. Segmented paging combines the two ideas. The program first picks a segment, then the segment's contents are stored in pages. The segment table tells where each segment's page table starts. The page table then tells where each page lives in physical RAM. This way we get the protection of segmentation. Different segments have different rights, and the flexible placement of paging. Pages can be scattered anywhere in RAM. Think of it as a library where each section segment has its own catalog page table that points to the exact shelf slots, physical pages where the books are placed. Segment lookup. Use the segment number S to fetch the segment base address SB and the segment limit SL from the segment table. Verify that the offset O is less than SL. Page lookup. Split the offset O into a page number P and a page offset delta using the page size P for a page size that is a power of 2. P equals O right shifted by log base 2 of P, and delta equals O bitwise and P minus 1. Use the segment's page table entry for page P to get the physical frame number F. Finally, compute the physical address PA. PA equals F times P plus delta. Or in one formula, combining the segment base SB when pages are contiguous inside a segment. PA equals SB plus P times P plus delta. If any check fails, such as offset out of segment limit, page number beyond the segment's page count, or page not present, a fault is raised. This two-level translation is like first finding the right chapter segment in a book, then finding the page within that chapter, and finally turning to the exact line offset on that page. Memory waste comes in two flavors. Internal fragmentation happens inside a page or segment when the allocated space is larger than what the program actually uses. For example, if a page is 4 kilobytes and a program needs 3 kilobytes, the remaining 1 kilobyte in that page stays unused. This is like buying a 12-inch pizza but eating only 9 inches. The rest is wasted. External fragmentation occurs when free memory is broken into many small holes that are too tiny to satisfy a large request. In pure segmentation, if you keep creating and deleting segments of different sizes, the memory can become a puzzle with many gaps. It is like a bookshelf where small books leave gaps that a big encyclopedia cannot fit into. Segmented paging reduces external fragmentation because pages are fixed size, so any free page can be used for any segment's page. However, internal fragmentation still exists at the page level, the unused part of the last page of a segment. The overhead also includes the segment table and per segment page tables, which take extra memory, similar to having extra index cards for each chapter in a library catalog. The translation look-aside buffer, TLB, is a small fast cache that stores recent virtual to physical translations. In segmented paging, there are 2 levels of translation, so the TLB can hold either full segment page frame entries, or just the page frame part after the segment has been resolved. When a lookup hits in the TLB, the CPU skips both the segment table and page table walks, saving time. Misses cause 2 memory accesses, one for the segment table entry, one for the page table entry, which can slow the program down. Because the TLB is limited in size, operating systems often design the segment and page sizes to make the most common accesses stay in the TLB. For example, keep the code segment small and its pages hot. The performance impact is similar to a librarian who remembers the location of the most frequently borrowed books, TLB hits, versus having to look them up in the catalog each time, TLB misses. Modern operating systems choose different trade-offs based on hardware and workload. Pure segmentation is simple to understand but suffers from external fragmentation. It is rarely used alone today. Pure paging eliminates external fragmentation, but loses the natural grouping of code data and stack, making protection harder. Segmented paging keeps the benefits of both. Each segment can have its own rights, while pages give fine-grained placement. However, it adds extra tables and complexity. Some OSes treat the whole address space as a single large segment and rely on paging only, simplifying the design. Others still use a flat segmentation model where the segment base is set to 0, and the limit covers the whole user space, effectively disabling segmentation, but keeping the hardware mechanisms for compatibility. The choice depends on how much protection granularity you need, how much memory overhead you can afford, and how well the hardware matches the design. It is like deciding whether to organize a library by genre segments, by fixed size shelves pages, or by a combination of both, considering the cost of extra catalog cards versus the ease of finding books.